Welcome to Distinctive Voices. I'm your host, Susan Marty. Please join me in welcoming to the Distinctive Voices podium, Dr. Kyle Cranmer.
Okay, thank you very much. It's really a pleasure for me to be here and very much an honor as well. It's my pleasure to tell you about the Large Hadron Collider, which I think is one of the most exciting things going on in science now and probably for this decade. So to start, I'll just tell you what is the LHC before we get into what we plan on doing and et cetera. And for that, I'll try to start with the big picture. So this is zooming in to Geneva, Switzerland, where there's an international laboratory called CERN. So there's Lake Geneva, and this big ring is about 13 miles around, and that's where the Large Hadron Collider, the accelerator part of it, goes. And this superstructure is some laboratories and things, and underground is where the interesting stuff happens. It's about 300 feet underground, and this is an enormous cavern that's been excavated underground, and this is the Atlas detector, which is one of the major experiments at the LHC, and which I'm a member of. And so now the person gives you some sense of scale. So it's about 120 feet long. It's the size of a pretty good sized building, and it's shoved full of electronics. So here is a picture of Atlas. Basically its most photogenic time. You saw the process of building it. What's not clear is this is all 300 feet underground. So assembling that was really like assembling a ship in a bottle. So there it is, beautiful, nice symmetry. You see this small person here, but it looks kind of empty. So what I don't want you to take away is the idea that it's hollow in some sense. It was later filled. Every nook and cranny was filled with electronics and sensitive devices of various sorts to try and measure the particles that are going to be flying out. So the best way to think about Atlas is like a big digital camera, okay? And we're taking not normal digital photographs, but three-dimensional digital photographs. And instead of something that you would get at Best Buy, this has several 100 million pixels, if you would like to say, and we take 40 million photos a second. So we are producing the largest data set that mankind has ever seen, and certainly it's the largest scientific single collaboration or undertaking probably in the history of science, which is very humbling. This is a picture of the CMS detector, which is our sort of competitor/brother on the other side of the ring. Typically there are more than one of these experiments so that we can kind of check we check to make sure there's not some systematic effect hiding in this very complicated device, but it's equally impressive. Ironically, the C for CMS stands for compact, which is, okay. So then the accelerator itself, which is what the LHC gets its name from, is shown here. So you see this very long tunnel. It's big enough to walk down, but it's not much bigger than that. This blue tube is a vessel that holds the actual accelerator, and this is a picture of where the beam of particles goes through. So this hole here is maybe this big. Okay, so the beam of particles is actually quite small, goes about 13 miles around. The protons are going almost the speed of light. There is 99.99999% of the speed of light, and they go around the ring about 11,000 times a second. So they're really whipping around, and to get that to happen, you need a lot of magnets and the magnets have to be very cold. So these are pictures of superconducting wires that the whole thing is made out of. If you go down to the smallest part, the smallest filaments these cables are made out of, there's enough cable to go to the to the sun and back 5 times. So there's a huge amount of superconducting cable, and the whole thing has to be kept just a couple of degrees above absolute zero. So it's argued, and I think it's probably true, that the LHC inside of that blue tube is the largest, or is the coldest extended structure in our galaxy. So it's hard to believe that you usually think of fireballs or something when you think of these collisions, but it's also the coldest place around. Okay, so why did we build the LHC? What are we trying to do? So this is just to try. This is some version of that answer. So what I've drawn here is an axis and it has this curious unit of GeV. So it's a unit of energy, and EV is for an electron volt. So if you took a 9-volt battery and you hooked up some wires to it, and you could somehow get an electron off a hydrogen atom, and you put it there and let go of it, it would be accelerated to the other side of that battery, and on the way it would have picked up 9 electron volts of energy. So a GeV is a giga electron volt, or a billion electron volts, and so chemical reactions are much smaller energy than that. Things like nuclear fission, what's powering nuclear power plants, or what's powering the sun, are less than one of these GeV units. And the sort of relevant thing that sets the scale of one GeV is the mass of a proton. So if you could take a hydrogen atom and take all of its mass and turn it into energy, it would be 1 GeV. And then the LHC is going to be about 14 trillion times the mass of that. And then you have the highest energy cosmic rays we've ever seen. So you might think the LHC would produce the highest energy particles we've ever seen, but actually we get bombarded by particles from outer space all the time, and rarely we get bombarded with very high energy particles. So the LHC has the energy of 1 proton will be similar to the energy of a fruit fly, which doesn't sound like much, but it's all packed into just 1 particle. The highest energy cosmic rays are more like a high-speed fastball from a baseball pitcher. And then there's a sort of holy grail type of energy scale for particle physicists, which is called the Planck scale. And I won't go into that too much, but basically it's where the ideas of gravity and quantum mechanics collide, and that's a place where we really ultimately would like to try and understand what's going on, but we're starting a little bit more modestly. So there's one more dot on this axis, and that is that star there. And the point is that we have a lot of reasons to believe that some sort of new phenomena is going to happen there. And the important thing to notice is the LHC has more energy than that dot. So we really think that we are going to see. There are a lot of ideas about what it might be. We don't really know, but there's a lot of hope that we're going to see something new and something very exciting at the LHC. Okay, so if you're going to appreciate new, you need to sort of appreciate the old. So let's just go through what we know about fundamental particles and what kinds of things we try to study as fundamental physicists. So let me start with something hopefully very familiar, which would be, for instance, this clicker in my hand or that block of wood. I think most people are familiar with the idea that it's made out of atoms. And maybe when you think about atoms, you think about the periodic table, which was from the sort of the mid to late 1800s when we started to organize all of the elements that we knew into the structure. And we started to see patterns and started to have some deeper insights about the fundamental building blocks of nature. Later, around the turn of the century, we understood that the atoms aren't fundamental, but they have a nucleus with an electron or several electrons orbiting around them. And then we understood that the number of electrons had a lot to do with the structure of that table. And so that's basically chemistry. And then with further study, we understood that the nucleus isn't fundamental, but is made out of protons and neutrons. So maybe some people have heard of that. And then we start to get to more esoteric things like quarks. Okay, so quarks are now we know to be the building blocks of protons and neutrons. So we know that in our current understanding, the quarks are treated as fundamental particles along with the electron that's orbiting around the atom. So those are our basic building blocks, and we put them into a table which is very much like the periodic table, but one of the nice things is it's quite a bit smaller. So we think that there are 6 types of quarks. They're the up, down, charm, strange, top, and bottom quarks. And then there's the electron, which we knew about from before. The electron has a heavier brother called the muon, and yet a heavier one called the tau, which are basically just copies of the electron but heavier. And then there are these kind of funny things called neutrinos, which are they're not very familiar to us because basically they fly through you and you don't see them, but we know that they're involved in radioactive decay and things like that. So these are basic building blocks of matter. And so now I pose this question, what about antimatter? So this is going to be one of the audience participation sections, is I want to take a bit of a poll about who thinks antimatter is real and who thinks it's just science fiction or something that, is theorized that maybe could exist. So who thinks it's real? Okay. Who thinks it's science fiction? Okay, great. So so it's interesting though because last year I taught a class of freshmen at NYU, and I asked them this question, and then I followed up with another question, which I'll ask you now, and then I'll reveal the results. So who thinks black holes are real, and who thinks that they're still sort of science fiction or yet to be confirmed? So who thinks they're real? Wow, you guys are, I guess, it's a biased audience, right? So what was interesting to me was that my undergraduates, maybe 20% thought antimatter was real, and 80% thought black holes were real. But antimatter has actually been around for a long time. Since the mid-30s, we've known about antimatter. And for instance, the P of the PET scan that you might have if you have some, the medical imaging, is for positron, which is the antiparticle of the electron. So we definitely know antimatter is there. And at least not all that long ago, I think the jury was still out as whether or not black holes really exist or if they were just some sort of mathematical abstraction. Okay, so the man on the left, I assume that's Albert Einstein, and on the right is Paul Dirac. So the reason that I say this here is to set the stage for something that I'll say later, which is that Albert Einstein, he proposed our special theory of relativity and later what's called the general theory of relativity. He told us this E equals mc squared, which is going to be very important in a little bit. But I'd like to focus on the theory of relativity because what relativity tells you is that there's some sort of very deep and fundamental relationship between space and time. So the speed of light in some sense can be thought of as a conversion factor between taking space and turning it into time or back and forth. And it's so you could call it somehow a symmetry of space and time. And what Paul Dirac realized was that symmetry, in addition to being pretty and various making good science fiction books, also predicted that for every particle like an electron there should be an antiparticle. So the mathematical reasoning that led to that is not so easy to explain, but the important point is that a symmetry of space-time implied that for every particle there should be a partner, which is the antiparticle. And we don't even show it on this table because in some sense there's no point in even adding it because you just know that every particle has an antiparticle, and so we just don't bother writing them down. Okay, so I'll come back to that point later. Okay, so now let's zoom out. So this is not what you might expect from a talk about the LHC. This is not the very small, so we're going to be the very big. So this is, it's kind of hard to see, but that's a picture of a galaxy. Here there's a star that just went supernova, so this star is exploding. Because of E equals mc squared, it's turning its mass into enough energy to outshine an entire galaxy for a small period of time. So this one star is outshining the whole galaxy. Any guesses to what this is? This is an image of the center of our galaxy, and those fuzzy dots are the best we could resolve some stars. And these stars are orbiting something. This one, the top left shows the years going by. Let me show that again. So 1992, we go to 2000 or something. They're orbiting something in the middle of our galaxy, and that something is a very massive black hole. So this is really, if you didn't believe it before, that's pretty good proof that there's something there. And so that's thought to be the black hole. So that's very nice. If we zoom out even farther, it turns out that galaxies are grouped into what are called clusters of galaxies. And here's a picture of a bunch of galaxies, a beautiful picture from the Hubble Space Telescope. So do you notice something kind of odd about this picture? There are these funny rings. There's certainly some kind of circle going on. So what is this funny structure? So it turns out that is another galaxy that's very, very far away. And this large cluster of galaxies is actually bending space and time in a way that light bends around that thing, and it ends up making it's like a lens. And so it's bending the light, and you see these funny rings. So it's one of the predictions from Einstein's general relativity. It's beautiful, makes you really scratch your head and think about what's going on out there. But what's nice is that this once you understand this, it allows you a technique to sort of X-ray what's going on inside of this cluster of galaxies. And in particular, allows you to measure the mass of that cluster of galaxies. So when you measure the mass of that cluster of galaxies and compare it to what you would expect it to be from all of the luminous matter, all the stars and things like that you see, it doesn't match. And so people start to think that maybe there's some sort of dark matter there. So this is a different picture which shows a different cluster of galaxies. So there's a bunch of stars or galaxies around. And these contours show where you think the mass is. So there's a lot of mass here, and there's a lot of mass here. And what's thought to have happened there is that there's actually two clusters of galaxies that collided over enormously long timescales. And so they've collided, and if you look to see not with your eye, but with different kinds of special telescopes, you see that there's a lot of hot gas there that's emitting light and radiation, and that's this reddish yellow color. So that's where most of the mass that we know about is from things like gas and stars and stuff like that. But the blue shows where you think most of the mass is from doing this, what's called gravitational lensing, what I was just showing you before. So what you see is they're separated. And so this was one of the strongest pieces of evidence that there really is some kind of mysterious substance out there, which is what we call dark matter. And the key point here is that we don't know what dark matter is. We know very well that it's there. We basically observe for sure that it's there, but it's not part of the standard model, this table of particles that I showed. So this is one of the mysteries that we're facing in the field. Okay, so if you then try to put everything together, you get this very humbling picture of what the universe on large scales looks like. So you really only have about 4% of the matter of the universe is stuff that I was telling you in the standard models, normal kinds of matter that we know about. About 23% of it is this mysterious dark matter, and then the overarching sum of it, 73%, is called dark energy, and that's something we know even less about. So I'm not going to address dark energy in this lecture, but it's good that we have more mysteries out there to solve in the future. But I will be addressing at least this sort of first quarter of the picture. Okay. So once you have this picture of what the universe is made out of, this is zooming out. This is a computer simulation, and the yellow dot in the middle is like a cluster of galaxies, and the purple stuff is dark matter. And this is basically our picture of what the universe looks like. And what's interesting, I'm just going to do that again real quick, is that at the beginning you see the familiar clumpy stuff that we're expecting. Here's the galaxies and other galaxies. They're spread out. But what you see is that the dark matter actually has this fantastic kind of filament-like structure that connects everything like some kind of amazing web. And we actually have a lot of evidence that this is how what the universe looks like on very, very large scales. So that's just kind of finalizing what we know. So here's our picture from the very largest scales to the very smallest scales, our table of what we think fundamental particles are made out of. But it's not just particles, they're also interactions. So when I say that I'm a particle physicist and people ask me what does that mean, I say I study fundamental particles and their interactions. So what kind of interactions do we have? Well, there's gravity. We know about, I'm being held to the floor and I'm being, pulled down to the earth, and the earth is being pulled to the sun because of gravity. So that's the most familiar. There's also the electromagnetic force, which is, when you play with magnets or things like that. All of telecommunications is based on the electromagnetic force. All of chemistry is based on the electromagnetic force. And then there are two forces which maybe you're not familiar with, which are called the strong and weak nuclear force. And you're not familiar with them because they're very short-ranged and they're basically only relevant inside of the nucleus of an atom. But they are very important for our understanding of nature because the weak force, for instance, is responsible for radioactive decay, and that's part of the chain of events that powers the sun. So if you like sitting out and basking in the nice California weather, you should think the weak force. And then you know maybe that opposite charges attract, right? So that's the electromagnetic force. But I'm pointing here to this nucleus. It has a bunch of protons, and they're all positively charged. So why are they sticking together in the nucleus? Shouldn't they fly apart? So the reason that they stay together is because of another force called the strong nuclear force. And it's aptly named strong because it's able to overcome that repulsive interaction and hold it all together. So that's basically our fundamental picture for the parts that we know about: 4 fundamental forces, and then these six matter particles. So this graph is showing that of those different kinds of particles, they don't all feel all of the forces. Some types of particles only feel certain kinds of forces. So for instance, the electron doesn't feel the strong force. So this table, I won't go through it, or this graph, I won't go through it, but it just shows that some particles participate in some interactions and some particles don't. So here we are back to the previous picture, and now this equation, which I'm certainly not going to try and explain, but is the standard model. Okay, it's written in a language which is called quantum field theory. Okay, it's a highfalutin mathematical framework that we use, but it's amazing that our fundamental description of basically everything that we know about can fit in such a concise form. It's very impressive. There's one thing that I'd like to say as just a remark here is that the standard model is sort of a specific theory, and this language of quantum field theory is a more general language for describing what other universes could have possibly looked like. And the heart of the whole thing, I would say, is this concept of symmetry. And so when you talk about these different fundamental forces, what happens is you basically just specify some sort of symmetry that you think your matter should have. And I won't go into it anymore, but then this language is like a big machine. And once you say what kind of symmetry is there, the machine turns the crank, and you get out equations like this, and you also get out different kinds of interactions. So the symmetries and the interactions are fundamentally linked in this very beautiful way. And so when you think about what else could be out there, there could be additional forces. Maybe it's not just 4 forces. Maybe there are other forces out there. Maybe the dark matter is just as complicated as the stuff that I've told you about. Maybe there's a lot of complexity there, and it has its own set of forces, and we just don't participate in those forces. So there's a lot of possibilities, and each one of those scenarios also brings with it some kind of beautiful statement about the underlying symmetries of nature, which I find very compelling. So the standard model, one of the things that I'd like to get across is this fantastically precise. There are parts about the theory, you can predict certain things to less than 1 part per million, which means that if I was going to, for instance, this is a slide I made for the Kavli Frontiers, which was held in Kunming, China. If I wanted to calculate the distance between New York and Kunming, it would be like me hitting, trying to figure out how hard I should hit my golf ball, and I would be able to make a hole in one. So that's how precise the theory is, which is hard to imagine. So it's, I think, compared to basically any other field of science, this is as precise as theory gets. So the big, I won't say sore thumb, but the big hole in the whole story is related to this man. This is Peter Higgs, and he did something very important for the Standard Model, which was to establish something about its mathematical consistency, which at that point had evaded everyone. And so here's his equation that he wrote down, which is part of that equation that I showed you before. And I don't know if you can see this kind of funny double well sombrero hat looking shape behind him, but I'll allude to that. That will be my graphical representation of Peter Higgs and his contribution. So it's an important part of the Standard Model, and it predicts there's a new particle called the Higgs boson, and that is the only unobserved particle of the Standard Model. So it's very important that we see it if we want to confirm the story that I'm telling you. And if we don't see it, then somehow we will be deeply confused about what's going on, because our theory is very precise and it's passed every test we've thrown at it. but we still haven't seen one of the key elements of the whole theory. So that's the hunt for the Higgs boson, and that's something that I've spent more than a decade preparing for and working on. So there's this issue about mathematical consistency, which probably doesn't mean much to anyone. The thing that grabs the headlines is to say that the Higgs boson is the origin of mass. Okay, so that sounds great. The thing is it also what does that even mean, right? I don't know if you try to internalize that, the origin of mass. Mass is such a fundamental property of how we think about the world. What does it even mean to say it's the origin of mass? So I tried to put together an analogy, which may or may not help. And so the idea is, for instance, I'm teaching to my freshman physics students, we do a lot of kind of problems with springs and blocks, and they move around. And so here's my block, and that's supposed to be mass. My block has some mass, and I've hooked it up to a spring, and that spring is supposed to represent a field, like the field that describes the electrons, okay, which is part of this quantum field theory, which we're not going to get into, obviously. So this is sort of the electron, and this is the electron's mass. Okay, now if I pull the block and I let it go, it wobbles back and forth. And the speed of that wobble is related to the stiffness of the string and the mass of the block. If you put a really heavy block on there, it's going to go slowly. If you put a really light block on there, it's going to go fast. Okay. So now, let's say I stick a flag onto my block, and I put a screen in the way, so you can't see the block anymore. And I pull on my block and I let go and it moves. So now all I get to see is the flag. So it moves. Even though I can't see the block or weigh it, I can still infer what the mass of the block is because I know the stiffness of my spring and I can see how fast it moves. Now I'm going to reach behind the screen and I'm going to fiddle with something, and you don't get to know what I did. And I'm going to do it again, and now it moves again, wobbles back and forth. So what are you going to infer? You're still going to infer that thing has the same mass just like you did before, right? Nothing has changed. Okay, so now I'm going to pull back the screen, and the idea here is the block is gone. There's no more mass as a fundamental concept. Instead, I've introduced a new spring, a funny spring, which is the Higgs field. And it's not like a normal spring because it's kind of like I stretched it out and, my son grabbed my slinky and pulled it and messed it all up. But when I hook it up to the original spring and sort of couple them together, everything looks the same from the outside. So that's my best attempt at an analogy of how the Higgs explains the origin of mass. You basically removed mass as a fundamental concept and replaced it with an interaction with the Higgs boson. Okay, so why do we use accelerators at all? We're trying to look at the inside of an atom, the very small things. Maybe you could just use a microscope. So microscopes can resolve things like cells. But the shortest distance they can resolve is related to the wavelength of the light that's going through the microscope. That's called the diffraction limit. So you would have to have a very high frequency light to be able to see something as small as an atom. And basically that's not going to happen. But when quantum mechanics came around, there was this idea that matter is not just like a particle. There's also a sort of corresponding wave-like description for matter. So that's this wave-particle duality, which maybe you've heard something about. And so you can think of particles as being matter waves. And the wavelength of these matter waves is 1 over the momentum of the particle. So if you have a very high momentum or high energy particle, its corresponding wavelength is very, very short. And the nice part there is that now that we're not talking about light, I'm talking about, say, an electron or something, I can accelerate it to very high energies, and thus it has a very small wavelength, and I can resolve what's going on inside of an atom. And so that's the basis for things like electron microscopes, and that's how you get pictures of, for instance, these are pollen grains, or you can start to actually resolve individual atoms with electron microscopes. But this is a small particle accelerator. Okay. So here's a picture of those pollen grains, and this is nature. This is real stuff. The thing that when you look at it, it's beautiful, right? So one of the things I'm going to try and get across here is that visually is that when you go to very small scales, symmetries are enhanced. Look at these things. They're amazing. And if you tried to build something like that, it would be very hard. So, and I don't know, maybe you've seen, like you think of bugs as dirty, but you've seen maybe pictures like this of very small bugs, but they actually look very clean, right? They're so small, dirt can't stick to them. So it's this funny picture that symmetries get enhanced, everything gets very clean and beautiful, and when you go even smaller, like to an individual atom, we think they're perfectly symmetric. So that's why these issues of symmetry become so important for fundamental particle physics. Okay, so the question was, why are we using accelerators? So the first part was just to get across the point that allows us to see very short distances. The other part is that, we could have waited for cosmic rays to rain down on us, but we have no control over them. And with accelerators, we have a lot of control. So the big revolution that happened in the 60s is when we started producing all sorts of new particles because we had accelerators. And at the time, there were these beautiful kinds of images like this made from cloud chambers, and they were taken, like real photographs were taken of these, and then people went and traced out the lines by hand and tried to figure out what was going on. Since then, just like everything, we moved from film to digital, and so later, that didn't take long. This was my Ph.D. advisor, and this is her advisor. And this was was actually right around when I was born, but this unfortunately was the last really exciting discovery for particle physics. This is something that was truly unexpected, and it's when this idea of quarks was taken very seriously. Before that, it was like some mathematical convenience. This is when people said, "Oh, these are real things," and that was very exciting. And Sam Ting and Bert Richter won the Nobel Prize for that. And then, around 1995, the top quark, which was the sort of last big building block of the Standard Model, was discovered, and it was exciting, but it was expected. And so the last thing that we're really searching for is the Higgs boson, but we've been looking for it for 20 years, and we still haven't found it. So, okay. So these are some pictures of using particle accelerators for previous discoveries. This is a discovery of the Z boson, which is one of the particles related to one of the forces. You won't be able to read it. I included it because I get a kick. It still says, this is a very famous photo for particle physicists, and up here, you can't read it, it says, very preliminary, which I think is funny because it's, 20 years later and it still says very preliminary. So this is a picture of Fermilab, which is in Chicago, which is another large particle accelerator, and this is where the top quark was discovered, and the LHC is now basically the flagship machine. And so what might we find there beyond the Higgs boson? Well, first, there is the Higgs, which is really one of the, to use the word flagship again, that's one of the flagship measurements that we hope to make, or discoveries to make at the LHC. One thing to say here is that the Higgs has associated to it one parameter, which is the mass of the Higgs boson itself, because somehow it interacts with itself and gives itself mass. So there's one knob of the Standard Model which is left free, and we don't know what that knob is. So we will have somehow completed the Standard Model if we discover the Higgs and measure its properties. But there are other things. There's something called supersymmetry, and supersymmetry is a challenge to explain, and that's why I spent a little bit of time when I showed Einstein and Dirac, because here I can just use the analogy is that what supersymmetry does is say that just like Einstein said space and time are related in some fundamental way and there's some interesting symmetry, supersymmetry is one additional symmetry that's being added to the picture. And just like Paul Dirac realized, if you have supersymmetry, this additional symmetry, you get an extra set of particles. You get an extra copy. So you had matter and antimatter, now you have particles and they're super partners. So there's an extra set of particles, but you would expect to already be familiar with those particles. You would expect to see them all the time. So somehow supersymmetry must be what we call it broken, and it's a broken symmetry which we don't understand why it's broken. We don't understand all sorts of things about supersymmetry, and maybe it's just not true. Maybe it's just not a property of nature. But if it is, it solves all sorts of problems. It solves one of the nagging problems of the Standard Model, which I haven't really been able to tell you about, which is called the naturalness problem. It predicts all these additional particles. It also points to, this is something won't really be able to explain, but this axis is somehow telling you the intrinsic strength of a force, and that changes depending on the energy that you're probing matter. And when you do that, you see that in the standard model, the forces, there are these lines. They're never the same intrinsic strength. But when you have supersymmetry, it looks like there's a magic energy where all of the forces combine and have the same intrinsic strength. So it's a big hint that maybe there's some sort of unified theory at very high energy. So when you hear about people talking about theories of everything or grand unified theories, this is what they're referring to, and supersymmetry is very much involved in that. So we're very interested in studying supersymmetry at the LHC. And then lastly, it also provides a candidate for dark matter. So all that stuff that I was telling you about that doesn't fit into the standard model, that's 24% of the universe, could be explained from supersymmetry. And if it is, we might make the particles of dark matter at the LHC and study their properties and see if they're consistent with what we see when we look into space. So that kind of ties in the LHC and adds to this analogy that not only is LHC the most powerful microscope that's ever been assembled, but it's also the most powerful telescope that's ever been assembled, because it's telling you about things that would have been taking place at the very beginning of the universe, shortly after the Big Bang, and telling you about the dark matter and all sorts of things that are relevant on a cosmic scale. Okay, so what other things might we see? So this is just going to be, we're just going to play sort of visual analogies here. This was my table that I showed before of the particles, and it's organized into 3 columns that we call generations. Maybe there's a 4th generation. So why not, right? So this is something that is very much studied and will be looked for. There's also just the idea of if things got smaller and smaller and smaller, why stop at quarks? Maybe there's substructure to the quarks. And so that's something we'll be studying. So the issue is that there's so many theories that us poor experimentalists or my graduate student trying to pick a project, says, how about this theory? He looks at me, and I'm like, how about this one? And there's so many possibilities for us to consider. He gets very, very frustrated. And this, I showed you one knob before. He's confronted with thousands and thousands of knobs. So it's very challenging. And that's what I'll start to finish. That's what I'll finish up with, is the sort of sociological and systemic problems that we face in doing science at such a large scale. But before I get to that, let me tell you a little bit about how the LHC actually works, because I talked about the sort of the theory and the motivation, but I want you to leave with some kind of gut picture of how it actually works. Okay, so this is, maybe I'll skip over a little bit, but these are these diagrams that were made famous from Richard Feynman, and they basically show that the particles are coming together. So this is space and time. So the particles are coming together, they collide, and for a short instant of time, because of E equals mc squared, you basically have a ball of kind of pure energy, and it's floating around in some way, trying to decide what it wants to do with its life, and then it decides, I want to decay into 2 muons. And then those 2 muons go flying out. So the important point is that the particles that are coming in are not necessarily the same as the particles that are going out, and that we can make new particles in these kinds of machines. And that's all because of E equals mc squared. So this is the cartoon picture of what's going on. These protons come and they collide and stuff flies out. And that's the level that I'll be talking about these interactions right now, is this very intuitive physical picture of stuff flying out. And so let's go back to Atlas. Here's our detector. It's made of lots of different components, and every one has a different role, does a different thing, and has a different technology behind how it works. But I'll just pick one and show you a little bit about how it works. So this is called the electromagnetic calorimeter. Okay, it measures the energies of particles like electrons. So your protons have come, they've collided, and there's a bunch of stuff flying out, and it's going to transverse through this detector. So now we're highlighting the electromagnetic calorimeter. We're going to turn it on its end. It has this interesting accordion-looking shape, and it's made out of lead. Okay? you might expect something fancy. There's a bunch of lead and stainless steel, and then between the lead and stainless steel, there's liquid argon. So it's a noble gas that's so cold that it's a liquid. And then on the sides of that, there are pieces of essentially copper, which are like an electric readout. And so those pieces of copper form essentially the pixels of our big digital camera. And so when an electron comes flying through, a very high energy electron that was produced, it hits the lead, and sometimes it makes more electrons, and it ends up making what we call a shower. It's a shower of particles, which is basically it's slowing down. And it takes that much lead to stop one of these particles. Otherwise, it would just keep on flying. So we don't make the thing bigger than we need to. It's that big because you need a lot of lead to stop it. And so then let's think about the more microscopic picture of what's going on. This is one little electron flying through. The blue is liquid argon. And what happens is that as these electrons plow through, they ionize the liquid argon. And so you have positive ions and negative electrons. The positive ions drift to one of the pieces of electric readout. The negative electrons go the other way. And then we just have wires essentially hooked up to it, and we look for a little electrical pulse. So it is a very physical device. It's not all mathematics. There's real amazing engineering that goes into designing these things, and it has a very kind of physical picture in the end. So here's one of the Atlas collaborators working on a different device, which is similar in principle. Here it's this time it's iron instead of lead, and instead of liquid argon, it's a special kind of plastic that when particles go through it glows. And so then these are fiber optic cables that collect the light, and then we basically measure the light that comes out. So that's how the digital camera works. And of course there are a lot of parts, and there are lots of other different kinds of technologies that go into taking these big three-dimensional digital photographs of the interactions. And the different kinds of particles behave differently in the detector. So they leave different patterns of energy deposits. And because of that, we can identify what kinds of particles hit us. And then our task is to take these pieces and try to reassemble what we think that what I started, that initial interaction was. And that's where, that's what we're after. And when I was introduced, it said that I worked on data analysis techniques. That's a lot of what I'm doing, is sort of this puzzle solving of trying to take all of these patterns and try and figure out what happened inside. Okay, so this I won't really go into. It's basically the idea that we're colliding, we're colliding millions and millions of times a second, and we couldn't save all of that data. So we actually throw away almost all of the data and only save the things that look like they're interesting. So now let me tell you a little bit about the turn-on of the LHC, which happened in September of 2008. This is a picture that basically shows this is time going up, and this little wobble is essentially the beam. So you see the wobble's there, and then it dies out. So the beam, this is when we first turned it on. It just lasted for a brief instant, and then we lost the beam. So they twiddled some knobs, and then we kind of caught the beam, but it was washing back and forth, and then we lost it again. So they twiddled some more knobs, and then we caught it, but it kind of slowly wobbled off, and then we lost it again. And then there's a timestamp here. This has been in about 10 minutes. And then finally, they caught it. So, it was amazing. After 10 years of building it, they turn it on, and it just worked. So it was really a fantastic moment until that happened, which was that there was a short, essentially, in one of the interconnects between these different magnets, and the short put a hole in one of the vessels that holds all the liquid helium, and there was a lot of force. These magnets weigh several tons, and it pushed them out of the way. So it was basically a small explosion. No one was hurt. So this was kind of where the problem happened. So they had to fix that, and that took a year. So then it started again in November of last year. This was the first collision that was seen by the LHC. People were amazingly happy after decades of preparation. Very happy. Is this point that the degree of enthusiasm seems to be kind of inversely related to the age. You see, not too happy, very happy. So this is just showing you what was happening when we looked at the black dots represent data and the yellow bars represent what we thought would happen. And there's a lot of structure in that. And so we did a very good job of predicting what was going to happen in terms of understanding how our detectors work. Here's a picture of one of the early events. You see these two particles. If you trace them back, they look like they came from right there, but then there's nothing before that. So what happened? What did happen was we made a particle that traveled for some distance and then decayed. So we expected that to happen. This is not something new. This was known about in the 60s. So you take these two particles, you put them together, and you get a nice peak. And that corresponds to the mass of this particle that you don't see. So that's what we're going to be doing when we look for new particles in a nutshell. It's just this was something we've known about from the 60s, but it's a good confirmation that everything's working. This is a little bit later. Now we're catching up to the 1980s when we made a Z boson, which is the carrier of the weak force. So you see these beautiful pictures of two particles flying through the detector. And then this just happened this summer, which is the production of top quarks. So this basically brings us up to 1995. And now we have re-seen every particle of the standard model that we know of, and now we are on the verge of discovery. So this is where it gets exciting. And amazingly, I told you about things we might see. Maybe we would see some sort of substructure. This summer, with just a few months of data, we've already started being able to exclude scenarios like this down to a certain scale. So this plot, which I won't explain, is just the result that came out this summer, which is basically excluding that there's any kind of substructure unless it's even smaller than what we're able to do right now. Okay, so then let me just end on some statement about what does the LHC foretell about the future of science. That's not supposed to be there. Okay, this is the Atlas collaboration, a small part of the Atlas collaboration. There are about 3,000 people now. I guess I should have updated these numbers. 3,000 people on Atlas from countries all around the world, and we somehow work together. And in fact, we even have to agree on our papers because all 3,000 of us sign it. So here's the first 2 pages of an Atlas paper. There I am. The 3rd and 4th page, the 5th and 6th page, 7th and 8th page, 9 pages of authors, right? So we're doing science at a very big scale. In addition to making it difficult to make your tenure case, it's hard to get along and decide about how things should work. This is a plot of the number of talks given in our collaboration as a function of year. So look at this. It's clearly growing exponentially. This year in 2010, we've given 44,000 presentations. It's amazing. So I spent a lot of time in meetings and things like that. So clearly you need some sort of system for gathering all this data and communicating all this kind of information. So I don't know if anyone knows this man. This is Tim Berners-Lee, and he invented the web. And he did it at CERN, and we gave it away to the world for free. So it's really, so the spin-offs, I mean, if you want to spin off, there you go. So it was totally unrealized how much it would change the world. And now there are different kinds of computing models that are being invented to try and deal with huge amounts of data that we're producing. And one of the aspects that I'm involved with is not so much about the computing aspect, but really about the communication aspect. Because we've put billions of dollars into these machines. People have spent decades of their lives building them. They consider that data to be theirs. So there's this attitude in the collaborations that is somehow proprietary data, and we don't want to just share it to anyone that comes along because we worked very hard for it. Then there are a lot of theorists that are coming up with models, which is, of course, why we built the whole thing in the first place, to test. So here's my picture of experimentalist who worked several years to try and build it, a theorist who's thinking about, fundamental particle physics, and this is, of course, the motivation for why we're doing this. And we've had a communication problem. Maybe I'm overstating it. I mean, we work pretty well together. Science goes on. But compared to what we're about to face with the LHC, we need a different form of communicating, I believe. And so one of the things that I've been working on is, for instance, a way of communicating information in a scientific context, which still kind of keeps data private and deals with issues of privacy or things like that, while still allowing science to go on and people to ask good questions about about what the data tells you. And I think that that these kinds of things are going to become more and more important in the future of science because, and I think physics is hitting it first, essentially. We have very precise theories. We have huge amounts of data. We have lots and lots of people involved. And that's just the direction that science is going in general. And so I think that the lessons that we're learning now are going to be relevant for basically all science in the future. And I think that that's a very exciting idea. So thank you very much.